Welcome to Sleepy Science Student, where we explore the cosmos one gentle whisper at a time. Tonight, we're going on a slow, peaceful journey into the very foundations of existence itself, the four fundamental forces that hold everything together. From the smallest quarks to the largest galaxies, these invisible architects shape every moment of reality, including this one, right now, as you settle into comfort. I hope this video isn't too interesting, though if it does happen to keep you awake, at least you'll be learning something fascinating about why anything exists at all, not the worst way to spend a sleepless night. Before we drift into the quiet architecture of the universe together, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this sleepy little channel grow and means more curious minds can find their way to these gentle explorations of science. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in London at midnight, or listening from a hammock in Melbourne at noon while the sun filters softly through the trees? Let me know in the comments. It's always such a joy to see the sleepy science community scattered gently across the globe, all wondering together. Now settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you like warm water flowing over smooth stones. Let your shoulders relax. Let your breathing slow down naturally. And as we begin this gentle voyage into the forces that make existence possible, remember, this video is for educational and relaxation purposes only. It's not intended as medical advice, a guide to building particle accelerators, or a replacement for actual physics classes, though it might make relativity feel suddenly very sleepy. Ready? Let's begin. Why does anything exist at all? It's a question that has drifted through human consciousness for as long as we've been able to look up at the stars and wonder. Why is there something rather than nothing? Why doesn't everything just collapse into chaos, or drift apart into emptiness, or simply cease to be? The answer, as it turns out, lies in four fundamental forces. Four invisible threads woven through the fabric of reality. Four principles that guide every interaction, every movement, every moment in the universe. They're so fundamental that without them, atoms wouldn't hold together. Stars wouldn't shine. You wouldn't exist to wonder about any of this. These forces have elegant names: gravity, electromagnetism, the strong nuclear force, and the weak force. Each one operates at different scales, following different rules, pulling and pushing in different ways. Together, they create a delicate balance that makes the universe not just possible, but stable. Predictable enough for life to emerge, yet dynamic enough for change to happen. Right now, as you lie there, all four forces are at work on your body. Gravity is gently pressing you into your mattress, a constant companion you rarely notice. Electromagnetism is crackling quietly through your neurons, carrying thoughts and sensations. The strong force is holding together every atomic nucleus in every cell. The weak force is quietly transforming particles deep inside you, a slow dance of decay and change happening beneath your awareness. You might think these forces are abstract concepts, mathematical ideas confined to textbooks and laboratories. But actually, they're the most intimate aspects of your existence. They're why your hand is solid enough to hold this device. They're why the earth doesn't fall into the sun. They're why stars burn, why atoms bond, why anything can touch anything else. The universe, in all its vastness, operates on surprisingly few rules. Just four forces, each with its own character, its own strength, its own domain. It's a bit like a cosmic symphony played by only four instruments, yet somehow producing all the complexity and beauty we observe. Let's pause for a moment and consider how remarkable this is. Everything you've ever experienced, every sunset, every conversation, every breath, emerges from the interplay of these four fundamental interactions. The universe isn't a collection of random events. It's a carefully orchestrated balance, where each force plays its part in the grand performance of existence. Scientists have spent centuries trying to understand these forces, to measure them, to predict their behavior. What they've discovered is both humbling and extraordinary. The forces don't just exist, they exist in precise ratios to one another. Change gravity by even a tiny amount, and stars wouldn't form. Alter electromagnetism slightly, and atoms wouldn't be stable. The universe seems remarkably fine-tuned, balanced on a knife's edge between existence and oblivion. Some researchers have wondered if there might be a fifth force hiding somewhere, waiting to be discovered. Others dream of a grand unified theory that would show how all four forces are actually different aspects of a single, more fundamental interaction. But for now, we have these four, and they're more than enough to sustain the entire cosmos. Tonight, we're going to explore each of these forces in turn, starting with the most familiar and moving gradually toward the strange and subtle. We'll discover how they were found, what they do, and why the universe would be utterly different, or perhaps impossible, without them. We'll travel from the centers of stars to the hearts of atoms, from the birth of galaxies to the chemistry happening in your brain right now. But there's no rush. We have time. The forces themselves operate on timescales from the infinitesimally brief to the eternal. Some interactions happen in trillionths of a second. Others unfold over billions of years. We'll move slowly through this landscape, taking our time, letting each concept settle gently before moving to the next. You don't need to understand everything. You don't need to memorize formulas or remember constants. Just let the story unfold, like watching clouds drift across a lazy afternoon sky. The universe has been operating according to these principles for nearly 14 billion years. It can wait patiently while we explore at a comfortable pace. So take a breath. Feel the weight of your body against the surface beneath you. That's gravity. Notice the warmth of your skin. That's electromagnetism at work. Molecules vibrating with energy. Consider the solid matter you're made of, held together by the strong force. Acknowledge the slow transformations happening inside you, guided by the weak force. You are, quite literally, a meeting place of all four fundamental interactions. The ancient Greeks believed everything was made of earth, air, fire, and water. They weren't entirely wrong, just looking at the wrong level. The true elements aren't substances, but interactions, not materials, but forces. And in understanding these forces, we come to understand why we're here at all, why the universe bothers to exist, and what keeps it from dissolving into meaninglessness. Let's begin our journey with the force that shaped our first understanding of the cosmos, the force that keeps our feet on the ground and the planets in their orbits. Let's talk about gravity. Gravity is perhaps the most familiar of all the forces, and yet it remains one of the most mysterious. You've felt it every moment of your life, that gentle but insistent pull toward the Earth's center. It's what makes things fall, what makes rain descend and rivers flow downhill, what creates the comforting weight of blankets on a cool evening. It's also, remarkably, the weakest of the four fundamental forces. If you've ever picked up a paperclip with a refrigerator magnet, you've witnessed electromagnetism easily overcoming the gravitational pull of the entire planet Earth. A small magnetic field can defeat the combined gravity of 6 trillion kilograms of matter. That's how weak gravity is at small scales. But weakness, in gravity's case, doesn't mean insignificance. Gravity has a superpower that the other forces lack. It never repels, only attracts. And it acts across infinite distances, growing weaker with distance, but never quite reaching zero. This means that given enough matter and enough time, gravity always wins in the end. Imagine gravity as a patient sculptor, working with the raw material of the universe on the grandest scales imaginable. It gathered the first clouds of hydrogen gas after the Big Bang, pulling them together gently, slowly, over millions of years. Those clouds became denser, warmer, more compressed. Eventually, they became the first stars. The ancient philosophers knew about gravity, though they didn't call it that. Aristotle believed heavy things naturally moved toward the center of the universe, which he thought was the Earth. He wasn't entirely wrong. Things do move towards centers of mass. He just had the wrong center in mind. Then along came Galileo, dropping objects from towers and rolling balls down inclined planes, demonstrating that gravity accelerates all objects equally, regardless of their mass. A feather and a hammer fall at the same rate in a vacuum, something astronaut David Scott famously demonstrated on the Moon in 1971, where there's no air resistance to interfere. But it was Isaac Newton who truly changed our understanding. Sitting in his garden in Woolsthorpe, possibly beneath an apple tree, though that story might be apocryphal, Newton realized that the force pulling apples to the ground was the same force keeping the Moon in orbit around Earth. The same principle operated everywhere, from the smallest stone to the largest celestial body. Newton's law of universal gravitation stated that every particle of matter attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. It's a mouthful, but the idea is beautifully simple. Bigger things pull harder, and things far apart pull less strongly. For more than 2 centuries, Newton's description worked perfectly. Scientists could predict planetary orbits, calculate tides, understand why the Earth bulges slightly at the equator. Gravity seemed solved, understood, complete. And then Einstein arrived and gently upended everything. In 1915, Einstein published his general theory of relativity, which reimagined gravity not as a force at all, but as a consequence of curved space-time. Massive objects don't pull on other objects across empty space, Einstein argued. Instead, they curve the very fabric of space and time around them, and other objects simply follow the straightest possible paths through this curved geometry. It's a bit like placing a bowling ball on a trampoline. The heavy ball creates a depression in the fabric, and if you roll a marble nearby, it will spiral inward, following the curve. The marble isn't being pulled by some invisible force, it's simply following the geometry of the curved surface. That's how gravity works in Einstein's view. Planets orbit stars because stars curve space-time, and planets follow those curves. This might sound like abstract philosophy, but it has real, measurable consequences. Light itself bends when passing near massive objects, something astronomers have observed during solar eclipses. Time runs slower in stronger gravitational fields, which is why GPS satellites have to account for relativistic effects. Their clocks tick faster than clocks on Earth's surface by about 38 microseconds per day. Without correcting for this, GPS systems would quickly become inaccurate. General relativity also predicted phenomena that seemed almost magical: black holes, regions where space-time is curved so extremely that nothing, not even light, can escape. For decades, these were considered theoretical curiosities. Now we've photographed them, observed stars orbiting around them, detected the gravitational waves they produce when they collide. Speaking of gravitational waves, let's talk about those for a moment. Einstein predicted that accelerating masses should create ripples in space-time itself, spreading outward at the speed of light like ripples in a pond. These waves would be incredibly weak, requiring fantastically sensitive instruments to detect. In September 2015, the LIGO detectors in the United States finally caught one, a gravitational wave produced by 2 black holes spiraling into each other 1.3 billion light-years away. The collision released more energy than all the stars in the observable universe combined for a brief fraction of a second. The wave that reached Earth was so small, it changed the length of LIGO's 4-kilometer arms by less than 1,000th the width of a proton. Yet it was detected, measured, analyzed. A new way of observing the universe had been born. Gravity shapes not just how things move, but how the universe itself is structured. Look up on a clear night, and you'll see stars, but you won't see the dark matter that dominates the gravitational landscape. Astronomers discovered that galaxies rotate too fast. their outer regions should fly apart given the visible matter alone. Something invisible, interacting only through gravity, must be holding them together. We call it dark matter, though transparent matter might be more accurate. It doesn't emit light, doesn't absorb light, doesn't interact electromagnetically at all. We know it exists only because of its gravitational effects. It outweighs normal matter by about 5 to 1, making up roughly 27% of the universe's total mass energy. What it actually is remains one of the great mysteries of modern physics. Then there's dark energy, an even stranger phenomenon. In the 1990s, astronomers discovered that the universe's expansion isn't slowing down as gravity would seem to require. Instead, it's accelerating. Something is pushing space itself apart, overwhelming gravity on the larger scales. We call this something dark energy, and it makes up about 68% of the universe. This means that the normal matter we can see and touch, stars, planets, people, everything, comprises only about 5% of the universe's total contents. We live in a cosmos dominated by invisible, mysterious substances and energies we barely understand. Gravity is our only tool for studying these cosmic mysteries. On human scales, gravity is the force that grounds us, quite literally. It's why we have up and down, why water pools in lakes rather than floating away, why we age. Our bodies evolved to work with gravity's constant pull. Astronauts in orbit experience bone loss and muscle atrophy because their bodies are no longer fighting gravity's gentle insistence. Gravity is also deeply personal. Every time you've jumped and returned to Earth, every time you've poured water and watched it fall, you've experienced this fundamental force. It's so constant that you rarely notice it, like background music playing softly through your entire life. Yet without it, nothing would hold together. The Earth would disperse into space, the sun would explode, the universe would be a thin soup of particles, never coalescing into anything interesting. Right now, as you rest there, gravity is pressing you gently downward. Feel it, that sense of weight, of being held. It's not just the Earth pulling on you, it's you pulling on the Earth too, with exactly the same force. Newton's third law applies to gravity. Every action has an equal and opposite reaction. You're attracting the Earth just as much as it's attracting you. It's just that the Earth is vastly more massive, so it doesn't move noticeably in response. Some physicists dream of a complete quantum theory of gravity, one that would explain how gravity behaves at the smallest scales, inside atoms, at the very moment of the Big Bang. So far, this has proven difficult. Gravity doesn't seem to play nicely with quantum mechanics. The mathematics that work beautifully for the other three forces stumble when applied to space-time curvature. Perhaps we need a revolution as profound as Einstein's to solve this puzzle. Or perhaps gravity is telling us something fundamental about the limits of our current understanding. But for tonight, we don't need to solve the mysteries of quantum gravity. We can simply appreciate gravity for what it is: the gentle sculptor, the patient force, the cosmic glue that holds galaxies together and keeps your feet on the ground. It's the weakest force, yet it dominates the universe. It's the most familiar, yet it remains the least understood at the deepest level. It's the reason there's a down to fall toward and an up to look toward when we gaze at the stars. Let's pause here for a moment. Take a breath. Feel the weight of your body, the gentle but insistent embrace of Earth's gravity. It's been with you every moment of your existence, and it will be there every moment until you return to dust. And even then, it will guide your atoms back into the ground, back into the cycle of matter and energy that makes up our world. Now let's turn our attention to a force that's stronger, more versatile, and present in almost everything you can see: electromagnetism. If gravity is the gentle sculptor working on cosmic scales, electromagnetism is the master craftsperson working at human scales and below. It's the force behind almost everything you can see, touch, feel, or experience. Light itself is an electromagnetic wave. The solidity of matter, the fact that your hand doesn't pass through the table, is electromagnetic. The colors of a sunset, the warmth of fire, the signal carrying this video to your device, all electromagnetic. Electromagnetism is not just one force, but two intimately related phenomena, electricity and magnetism. For centuries, they were thought to be separate. People knew about lodestones that attracted iron. They knew about amber that could attract hair when rubbed, but these seemed like different mysteries. The ancient Greeks noticed that rubbing amber, electron in Greek, created a strange attractive force. Static electricity, we call it now. They had no idea they were observing one of the fundamental forces of nature. To them, it was a curiosity, a parlor trick, nothing more. Magnetism was equally mysterious. The Chinese discovered that lodestones aligned themselves north-south and began using them for navigation, perhaps as early as the 1st century CE. Sailors learned to trust these magnetic compasses, even if they didn't understand why they worked. There were theories, of course. Perhaps magnetism was a kind of soul that lived in the stones. Perhaps invisible effluvia streamed from magnets, pulling iron toward them. Then, in 1820, a Danish physicist named Hans Christian Ørsted made a discovery that would change everything. During a lecture demonstration, he noticed that when electric current flowed through a wire, a nearby compass needle moved. Electricity and magnetism weren't separate phenomena. They were connected. A flowing electric charge creates a magnetic field. Within a few years, other scientists had explored this connection further. If electricity could create magnetism, could magnetism create electricity? In 1831, Michael Faraday in England and Joseph Henry in America independently discovered electromagnetic induction. A changing magnetic field creates an electric current. This principle underlies every electric generator and motor ever built. It's how we convert mechanical energy into electrical energy and back again. But it was James Clerk Maxwell, a Scottish physicist with remarkable mathematical insight, who truly unified electricity and magnetism into a single, coherent theory. In the 1860s, Maxwell wrote down 4 equations, now called Maxwell's equations, that completely describe electromagnetic phenomena. These equations are among the most beautiful and powerful in all of physics. Maxwell's equations revealed something extraordinary. Light is an electromagnetic wave. Oscillating electric and magnetic fields, perpendicular to each other and to their direction of travel, propagating through space at the speed of light. What we see with our eyes is just a small slice of the electromagnetic spectrum, visible light ranging from about 400 to 700 nanometers in wavelength. But the electromagnetic spectrum extends far beyond what we can see. Radio waves, with wavelengths from millimeters to kilometers, carry communications and let us peer through cosmic dust to observe the universe. Microwaves heat our food and carry cell phone signals. Infrared radiation is heat, what you feel when you stand near a fire or in sunlight. Ultraviolet radiation gives us sunburns and makes certain materials fluoresce. X-rays penetrate soft tissue and reveal our bones. Gamma rays are produced in nuclear reactions and by the most energetic events in the universe. All of these, from radio to gamma, are fundamentally the same phenomenon, just with different wavelengths and energies. It's a bit like how sound can range from deep bass to high treble, all sound waves but experienced very differently. The electromagnetic spectrum is a rainbow that extends infinitely in both directions, beyond what our eyes can perceive. Electromagnetism is also responsible for chemistry, which is really just the study of how electrons interact. Atoms bond together because of electromagnetic forces between their electrons and nuclei. When you smell a flower, volatile molecules are drifting into your nose and interacting electromagnetically with receptors, triggering nerve signals, also electromagnetic, that your brain interprets as fragrance. The food you eat provides energy through chemical bonds. electromagnetic in nature. The structural proteins in your muscles, the DNA in your cells, the calcium in your bones, all held together by electromagnetic forces. Life itself is an electromagnetic phenomenon, a dance of charged particles following the rules that Maxwell discovered. Every color you've ever seen comes from electromagnetism. The blue of the sky happens because air molecules scatter blue light more than other colors, a purely electromagnetic effect. The red of a rose comes from molecules in the petals that absorb most wavelengths but reflect red. The green of leaves is chlorophyll absorbing blue and red light to power photosynthesis, reflecting green. You might think solid matter is, well, solid, but actually it's mostly empty space. An atom is like a cathedral, with a fly in the middle representing the nucleus and a few gnats buzzing around the outer walls representing the electrons. What makes matter feel solid is electromagnetic repulsion. The electrons in your hand repel the electrons in the table, and this repulsion is so strong on small scales that objects can't penetrate each other. You're not really touching anything, you're floating about a nanometer above it, held up by electromagnetic fields. The strength of electromagnetism is difficult to overstate. It's about 100 million trillion times stronger than gravity. A single electron and proton in a hydrogen atom attract each other electromagnetically with a force that, while tiny in absolute terms, is vastly greater than their gravitational attraction. If you could somehow turn off electromagnetism and leave only gravity, every atom in your body would immediately explode, its electrons and nucleus no longer bound together. Lightning is a dramatic demonstration of electromagnetic force. Charge separation in storm clouds creates enormous electric potentials, sometimes over 100 million volts. When the field becomes strong enough, air, normally an insulator, breaks down, and charge flows in a blazing arc from cloud to ground or cloud to cloud. The temperature in a lightning bolt can reach 30,000 Kelvin, 5 times hotter than the surface of the sun. The rapid heating creates a shock wave we hear as thunder. Electricity in your home is electromagnetic force doing work at a more controlled pace. Electrons drift slowly through wires, actually quite slowly, just millimeters per second. But the electromagnetic signal propagates at nearly the speed of light. When you flip a switch, the lamp turns on almost instantly, not because electrons race from the switch to the bulb, but because the electromagnetic field change propagates quickly, nudging electrons throughout the circuit into motion. Magnetism, too, has practical applications we rely on every day. Hard drives store data using tiny magnetic domains. Speakers use electromagnets to convert electrical signals into vibrating diaphragms that create sound waves. Magnetic resonance imaging machines use powerful magnetic fields and radio waves to peer inside your body without harmful radiation. The Earth itself has a magnetic field, generated by electric currents in the molten iron outer core. This field protects us from the solar wind, a stream of charged particles flowing out from the sun. When these particles interact with Earth's magnetic field, they're channeled toward the poles, where they collide with atmosphere molecules and create the aurora borealis and aurora australis, the northern and southern lights. Those shimmering curtains of green, red and purple are visual displays of electromagnetic forces at work. Animals have learned to sense and use electromagnetic fields. Sharks and rays have organs called ampullae of Lorenzini that can detect tiny electric fields, helping them find prey buried in sand. Migratory birds appear to sense Earth's magnetic field, possibly through special proteins in their eyes that are affected by magnetic fields. Sea turtles navigate using magnetic maps, sensing not just the field's direction, but its strength, allowing them to determine their position. Some scientists have wondered whether humans have any magnetic sense. There's some evidence that we might, very weakly, though we're certainly not consciously aware of it. We evolved as visual creatures, relying on electromagnetic radiation, light, rather than magnetic field detection. Still, every thought you have involves electromagnetic signals cascading through your neural networks. Your brain generates electromagnetic fields strong enough to be detected outside your skull. That's what an EEG measures. Right now, electromagnetic forces are at work throughout your body. Sodium and potassium ions are flowing across cell membranes, creating electrical potentials. Nerve signals are racing along neurons at speeds up to 120 meters per second. Your heart is beating to an electrical rhythm coordinated by specialized cells. Even your sense of touch as you lie there is mediated by mechanoreceptors that convert pressure into electrical signals. Photons, particles of light, are also electromagnetic in nature. They're ripples in the electromagnetic field, quantum packets of energy with zero mass that travel at the ultimate cosmic speed limit. Every photon that hits your eye has traveled at light speed from its source, whether that's a lamp across the room or a star billions of light years away. The photons from distant stars have been traveling for eons, and when they finally strike your retina, they trigger an electromagnetic cascade that you experience as seeing. Electromagnetism is also the force behind the technology that's made modern civilization possible. Electricity generation and distribution, telecommunications, computing, medical imaging, and countless other technologies rely on our understanding of electromagnetic principles. Maxwell's equations, written in the 1860s, laid the groundwork for the electronic age that began decades later and continues today. There's something almost musical about electromagnetism. Radio waves oscillate hundreds of thousands to billions of times per second. Light oscillates hundreds of trillions of times per second. It's all vibration, all rhythm, all waves moving through space. The universe is humming with electromagnetic radiation at every frequency. A cosmic symphony playing constantly, mostly inaudible and invisible to us, but detected by our instruments, and, in small ways, by our bodies. Let's pause for a moment. Take a breath. Look around, even if just in your mind's eye. Everything you see is electromagnetic radiation that's traveled from objects to your eyes. The warmth you feel is infrared radiation and molecular vibrations. The thoughts you're having right now are electromagnetic impulses. You are, in a very real sense, an electromagnetic being living in an electromagnetic world. Electromagnetism is stronger than gravity, more diverse in its effects, and responsible for the rich complexity of chemistry and biology. But it's not the strongest force, not even close. For that, we need to journey inward, past atoms, into the nucleus itself, where protons and neutrons huddle together against enormous repulsive forces. We need to talk about the strong nuclear force, deep inside every atom. In a nucleus smaller than 100,000th the size of the atom itself, protons huddle together in what should be impossible proximity. Each proton carries a positive charge, and like charges repel. Electromagnetically, protons should blast apart with tremendous force. The electromagnetic repulsion between two protons touching each other is enormous, and yet nuclei hold together. Atoms exist. Matter is stable. Something must be overpowering electromagnetism at these tiny distances. That something is the strong nuclear force, and it's the most powerful force in nature. At distances smaller than about a femtometer, 1/4,000,000th of a meter, the strong force is roughly 100 times more powerful than electromagnetism, which is already vastly more powerful than gravity. It's the nuclear glue that holds matter together at the most fundamental level. Without the strong force, there would be no atomic nuclei. Without nuclei, there would be no atoms. Without atoms, there would be no chemistry, no complexity, no life. The universe would be a thin soup of electrons and hydrogen nuclei, single protons, drifting apart forever. The strong force is, quite literally, what makes the material world possible. The story of how we discovered this force is one of the great detective stories in physics. In the early 20th century, physicists were probing atoms, firing particles at them, observing what happened. Ernest Rutherford, working at the University of Manchester around 1911, conducted an experiment that revealed the atomic nucleus. He fired alpha particles, helium nuclei, at thin gold foil and found that most passed through, but some bounced back at large angles. This was shocking. As Rutherford later said, it was like firing a cannonball at tissue paper and having it bounce back at you. The only explanation was that atoms had a tiny, dense nucleus carrying almost all the mass. But this created a problem. How could positive charges cluster so densely without flying apart? In the 1930s, physicists realized that a new force must exist, one that only operates at nuclear distances but is powerful enough to overcome electromagnetic repulsion. They called it the strong force, or sometimes the strong nuclear force, and gradually worked out its properties through experiments with particle accelerators and observations of nuclear decay. The strong force has some peculiar properties. Unlike gravity or electromagnetism, which extend across infinite distances, the strong force has a very short range. Beyond about 1 to 3 femtometers, it effectively drops to zero. This means it only affects particles that are essentially touching at nuclear scales. It's a bit like trying to bind books together with glue that only works if the books are pressed directly against each other. Another strange property: the strong force doesn't care about electric charge. It binds protons to protons, protons to neutrons, and neutrons to neutrons with roughly equal strength. It's indiscriminate in that way. As long as you're a nucleon, either a proton or a neutron, the strong force will bind you to other nucleons. But perhaps the strangest property is this: the strong force gets stronger as you try to pull quarks apart. Most forces work the opposite way. Gravity weakens with distance. Electromagnetism weakens with distance. But the strong force increases with distance, at least up to a point. It's like a rubber band that gets harder to stretch the more you pull on it. Quarks are the truly fundamental particles here. Protons and neutrons aren't indivisible. They're each made of 3 quarks bound together by the strong force. Protons contain 2 up quarks and 1 down quark. Neutrons contain 1 up quark and 2 down quarks. These quarks are held together by particles called gluons, which are the carriers of the strong force, much like photons are the carriers of electromagnetism. The theory describing all of this is called quantum chromodynamics, or QCD for short. It's a wonderfully appropriate name because quarks carry a property whimsically called color charge, though it has nothing to do with actual colors. Quarks come in 3 color charges: red, green, and blue. Antiquarks carry anti-colors: anti-red, anti-green, and anti-blue. Gluons carry combinations of color and anti-color. The rules of QCD state that only colorless combinations can exist in isolation. 3 quarks with different colors combine to make a colorless proton or neutron. A quark and an antiquark with opposite colors combine to make colorless particles called mesons. But you can never isolate a single quark. Try to pull one out of a proton and the energy you put into separating it will instead create new quark-antiquark pairs. You'll end up with 2 or more colorless particles, but never a lone quark. This phenomenon is called confinement, and it's one of the deep mysteries of the strong force. We can't quite prove mathematically why confinement must occur, though we observe it consistently. Single quarks simply don't exist in nature. They're always bound together in groups that balance out their color charge. The strong force is responsible for one of the most important processes in the universe: nuclear fusion. Inside stars, hydrogen nuclei, protons, overcome their electromagnetic repulsion through quantum tunneling and the intense pressure and temperature of the stellar core. When they get close enough, the strong force takes over, binding them together. This releases energy, a lot of energy, which is why stars shine. The sun fuses about 600 million tons of hydrogen into helium every second, converting roughly 4 million tons of mass into energy, according to Einstein's famous equation, E1mc2. The energy released powers the sun's light and heat, which travels through space and warms our planet, drives our weather, powers photosynthesis, and makes life possible. All of this ultimately depends on the strong force binding nuclei together in the hellish furnace at the sun's core. Different elements form through different fusion processes. Hydrogen fuses to make helium. Helium fuses to make carbon and oxygen. Heavier elements form in more massive stars through further fusion reactions. Iron is the end point of this process. Fusing iron requires energy rather than releasing it. Elements heavier than iron are formed in supernova explosions and neutron star collisions, where conditions are extreme enough to force nuclei together, despite the energy cost. Every atom of carbon in your body, every atom of calcium in your bones, every atom of iron in your blood was forged inside a star and then scattered into space when that star died. The strong force made those atoms possible. You are, quite literally, made of star stuff, held together by the strongest force in nature. Nuclear fission is the strong force working in reverse, in a sense. Very heavy nuclei like uranium-235 are barely stable. They're so large that the electromagnetic repulsion between all those protons nearly overcomes the strong force holding the nucleus together. Hit such a nucleus with a neutron, and it can split into two smaller nuclei, releasing energy and more neutrons in the process. This is how nuclear reactors and nuclear weapons work. The energy released comes from the difference in binding energy between the original heavy nucleus and the resulting lighter nuclei. The products are more tightly bound, held together more efficiently by the strong force. So the difference in energy is released, largely as kinetic energy of the fission fragments. The strong force also explains why some elements are radioactive. Very heavy elements like uranium and plutonium have nuclei so large that they're metastable. The strong force can't quite hold them together indefinitely. Eventually, through quantum processes, they decay, emitting alpha particles, beta particles, or gamma rays, gradually transforming into lighter, more stable elements. Even stable nuclei aren't quite static. The protons and neutrons inside are constantly interacting, exchanging virtual mesons, short-lived particles that mediate the strong force between nucleons. It's a dynamic, energetic environment in there, a tiny realm of constant activity far below the scale we can directly observe. You might think nuclear physics is abstract, far removed from daily life, but actually, the strong force touches your life in numerous ways. Medical isotopes used in diagnostics and treatment rely on nuclear properties. Smoke detectors contain tiny amounts of americium-241, which emits alpha particles that ionize air and allow current to flow. Carbon-14 dating uses the radioactive decay of carbon to determine the age of organic materials. Nuclear power plants provide about 10% of the world's electricity, all from controlled nuclear fission. And of course, the strong force is what makes the stars shine, including our sun. Without it, the universe would be cold and dark, lit only by the faint glow of gravitational collapse, if even that. There would be no fusion, no starlight, no warmth, no energy source for life to emerge around. Right now, as you rest there, the strong force is at work in every nucleus of every atom in your body. It's operating on scales so small you could never perceive it directly, yet it's absolutely essential to your existence. Without the strong force binding nuclei together, you would simply cease to exist in any meaningful sense. The atoms that make up your body would fly apart, matter would be impossible, and the universe would be a very different, very empty place. Scientists are still exploring the mysteries of the strong force. Particle accelerators like the Large Hadron smash protons together at incredible energies, briefly recreating conditions that existed microseconds after the Big Bang, when quarks and gluons moved freely in a hot, dense plasma. By studying these collisions, physicists hope to understand QCD more deeply, to solve puzzles about confinement, and perhaps to discover new physics beyond our current theories. The strong force is powerful, but it's also beautifully constrained. Its short range means it only matters at nuclear scales. It makes atomic nuclei possible without causing everything to collapse into a single giant nucleus. It's perfectly calibrated to create a universe with diverse elements, with stable matter, with the building blocks of complexity. Let's take a breath here. Consider the hierarchy of forces we've explored so far. Gravity, the weakest, shapes the universe at the largest scales. Electromagnetism, much stronger, governs chemistry and biology. The strong force, strongest of all, holds the nucleus together and powers the stars. Each operates in its own domain, rarely interfering with the others, creating a delicate balance that makes reality stable and comprehensible. But there's one more force we haven't discussed yet, and it's perhaps the strangest of all. It's called the weak force, and while it's stronger than gravity, but weaker than electromagnetism and the strong force, its effects are subtle, slow, and absolutely essential to the universe we inhabit. Let's explore this quiet transformer, this gentle catalyst of change deep inside atomic nuclei. The weak force is the oddest member of our quartet of fundamental interactions. It doesn't hold anything together like gravity or the strong force. It doesn't create the rich phenomenology of chemistry and light like electromagnetism. Instead, the weak force causes particles to transform into other particles. It's responsible for certain kinds of radioactive decay, for processes inside the sun that allow fusion to proceed, and for the fact that you exist at all. Without the weak force, nuclear fusion in stars would happen very differently. The sun wouldn't shine quite the way it does. The early universe wouldn't have evolved the way it did. The balance between matter and antimatter would be different, and quite possibly, there would be no matter left at all, just energy dissipating into an empty cosmos. The weak force is subtle, but its absence would be catastrophic. The weak force was discovered through observations of beta decay, a form of radioactivity where a neutron transforms into a proton, emitting an electron and an antineutrino in the process. For years, this process puzzled physicists. Energy didn't seem to be conserved. Wolfgang Pauli proposed in 1930 that an invisible, nearly massless particle must be carrying away the missing energy. He called it the neutrino, Italian for little neutral one. Neutrinos are ghost particles, interacting so weakly with matter that they pass through the entire Earth as if it weren't there. Every second, trillions of neutrinos from the sun pass through your body, and you never notice. Only very occasionally does a neutrino interact with matter, and when it does, it's through the weak force. The weak force operates through the exchange of particles called W and Z bosons. These are extremely massive particles, about 80 to 90 times the mass of a proton. Because they're so heavy, they can't travel far before decaying. This gives the weak force an extremely short range, even shorter than the strong force, about 0.001 femtometers. It's a force that only matters at the smallest scales, deep inside atomic nuclei and subatomic particles. The peculiar thing about the weak force is that it can change the flavor of quarks. Remember that protons contain up quarks and down quarks. The weak force can transform an up quark into a down quark or vice versa. This is how beta decay works. A down quark in a neutron transforms into an up quark, changing the neutron into a proton and emitting a W boson that immediately decays into an electron and an antineutrino. This flavor-changing ability is unique to the weak force. The strong force binds quarks together but doesn't change their type. Electromagnetism interacts with charged particles but doesn't alter their fundamental nature. Only the weak force can reach into a particle and change what kind of particle it is. In the sun's core, the weak force plays a crucial role in the fusion process. When two protons overcome their electromagnetic repulsion and get close enough for the strong force to bind them, you might expect they'd form a helium-2 nucleus. But helium-2 is unstable. Instead, one of the protons immediately transforms via the weak force into a neutron, creating deuterium, a heavy isotope of hydrogen. This transformation releases a neutrino and a positron. This step, governed by the weak force, is the slowest step in the solar fusion chain. It's the bottleneck that determines how fast the sun burns its fuel. A typical proton in the sun's core waits billions of years before undergoing this transformation. This slowness is actually fortunate for us. If the weak force were stronger, the sun would burn through its hydrogen fuel much faster, and it wouldn't live long enough for complex life to evolve on Earth. The weak force is also responsible for the violation of certain symmetries in nature. For most of physics history, scientists assumed that nature was perfectly symmetric. If you reversed left and right, or swapped particles with antiparticles, or reversed time, the laws of physics should look the same. But experiments in the 1950s and 1960s showed that the weak force violates these symmetries. Parity violation, the fact that the weak force distinguishes between left and right, was discovered by Chien-Shiung Wu in 1957. She showed that beta decay produces electrons preferentially in one direction relative to the nuclear spin. The universe, at least where the weak force is concerned, has a handedness. It's not perfectly symmetric between left and right. The weak force also violates CP symmetry, the combined symmetry of charge conjugation and parity. Matter and antimatter don't behave exactly the same way under weak interactions. This tiny asymmetry, just a difference of a few parts per billion, is thought to be why the universe contains more matter than antimatter. If the weak force treated matter and antimatter perfectly symmetrically, they would have annihilated each other completely in the early universe, leaving only energy behind. So in a sense, you exist because the weak force violates symmetry. That tiny imbalance allowed some matter to survive the mutual annihilation with antimatter in the first fractions of a second after the Big Bang. Everything we see, every star, planet, and living creature, comes from that small surplus of matter that the weak force's asymmetry preserved. Neutrinos, those ghost particles, come in three flavors: electron neutrinos, muon neutrinos, and tau neutrinos, associated with three different types of charged leptons. Remarkably, neutrinos can oscillate between these flavors as they travel through space. A neutrino born as an electron neutrino might later be detected as a muon neutrino. This oscillation is only possible because neutrinos have mass, tiny mass, but not zero, and because the weak force couples to all three flavors. The discovery of neutrino oscillations earned the Nobel Prize in Physics in 2015. It revealed that neutrinos are even stranger than previously thought, and that the standard model of particle physics needed revision. We now know neutrinos have mass, though we don't yet know exactly how much. These nearly massless particles racing through the cosmos at nearly light speed represent one of the frontiers of modern physics. The weak force is also involved in processes happening inside your body right now. Radioactive isotopes of potassium and carbon undergo beta decay in your tissues constantly, though in tiny amounts. These decays contribute a small fraction of your background radiation exposure. They're relics of ancient supernovae, unstable isotopes incorporated into your body through food and drink, slowly transforming through weak interactions. Some radioactive isotopes used in medicine rely on weak force processes. Positron emission tomography, PT scans, use isotopes that undergo beta plus decay, emitting positrons that immediately annihilate with electrons, producing gamma rays that medical instruments can detect. These scans help diagnose cancer, heart disease, and neurological conditions. The weak force, subtle as it is, has become a tool for healing. You might think the weak force is too obscure to matter in daily life. But actually, it's essential to the nuclear processes that power the sun, which provides nearly all the energy on Earth. Plants photosynthesize using sunlight. Animals eat plants or other animals. And the energy that powers your muscles, your thoughts, your heartbeat, all traces back to fusion reactions in the sun that required the weak force to proceed. The weak force also governs the stability of matter. Some elements have multiple isotopes, versions with different numbers of neutrons. Many of these isotopes are unstable and decay through weak interactions, gradually transforming into stable elements. Carbon-14 decays into nitrogen-14. Potassium-40 decays into argon-40. These slow transformations create natural clocks that geologists and archaeologists use to date rocks and artifacts. Without the weak force, beta decay wouldn't occur. Neutrinos wouldn't interact with anything at all. In fact, they might not exist. The fusion process in stars would have to work differently, if it worked at all. The balance between matter and antimatter in the early universe might have been different, possibly leaving us with no matter at all. The weak force is subtle, operating at tiny scales, producing changes that take billions of years or happen in billionths of a second. It's not dramatic like lightning or powerful like nuclear fusion. It's quiet, patient, gentle, yet it transforms the very substance of reality, one particle at a time, enabling the universe to be dynamic, complex, and interesting. Let's pause once more. Take a breath. We've journeyed through all four fundamental forces now. Gravity shaping space-time on cosmic scales, electromagnetism creating the visible world, the strong force binding nuclei and powering stars, and the weak force transforming particles and preserving matter. Each force operates in its own domain, following its own rules. Yet together, they create a universe of extraordinary richness and balance. But how do these forces relate to each other? Are they truly separate? Or might they be different aspects of something more fundamental? Let's explore the grand quest to unify the forces, the search for a theory of everything that could reveal the deepest secrets of reality. Physicists have long dreamed of unification. Surely, they reasoned, the four fundamental forces aren't truly independent. Surely there's some deeper principle, some more fundamental law, that explains why these particular forces exist and why they have the properties they do. This dream has driven some of the most profound discoveries in physics, and it continues to inspire research at the frontier of theoretical and experimental science. The first great unification happened in the 19th century, when Maxwell showed that electricity and magnetism were two aspects of a single electromagnetic force. Before Maxwell, these seemed like separate phenomena. After Maxwell, it was clear they were intimately connected, different manifestations of the same underlying field. This was a profound insight, and it set the template for future unification attempts. In the 1960s and 1970s, physicists achieved another unification, this time between electromagnetism and the weak force. Sheldon Glashow, Abdus Salam, and Steven Weinberg independently developed a theory showing that these two forces were actually different aspects of a single electroweak force. At high enough energies, like those in the early universe, electromagnetism and the weak force would be indistinguishable, unified into one force. The electroweak theory predicted the existence of the W and Z bosons, which were subsequently discovered at CERN in 1983. It also predicted the Higgs boson, a particle associated with a field that gives other particles their mass. The Higgs was finally discovered in 2012, also at CERN, completing the standard model of particle physics and confirming the electroweak unification. This was a remarkable achievement. Two forces that seem very different at everyday energies, electromagnetism extends across infinite distances, while the weak force operates only at subatomic scales, turn out to be unified at higher energies. The difference between them emerges through a process called spontaneous symmetry breaking, where the unified electroweak symmetry breaks down into separate electromagnetic and weak forces as the universe cools. It's a bit like water freezing into ice. Liquid water looks the same in all directions. It has no preferred orientation. But when it freezes, the ice crystals have a structure, a particular arrangement of molecules. The symmetry is broken. Similarly, the electroweak symmetry is broken at low energies, creating the distinct electromagnetic and weak forces we observe today. Naturally, physicists wondered, could the strong force also be unified with the electroweak force? This led to theories called grand unified theories, or GUTS. These theories propose that at extremely high energies that existed only in the first moments after the Big Bang, all three forces, strong, weak, and electromagnetic, were unified into a single force. Grand unified theories make testable predictions. Many predict that protons should eventually decay, though with half-lives far longer than the current age of the universe. Experiments have searched for proton decay in underground detectors filled with ultra-pure water, watching for the telltale flash of light that would signal a proton transforming into lighter particles. So far, no convincing evidence of proton decay has been found, which constrains but doesn't entirely rule out guts. These theories also predict the existence of magnetic monopoles, isolated north or south magnetic poles, unlike the north-south pairs we always see in magnets. Despite searches, no magnetic monopoles have ever been detected. This either means they're incredibly rare, or our gut theories need revision, or perhaps unification doesn't happen quite the way these theories suggest. The real challenge is unifying gravity with the other three forces. Gravity stands apart, described by Einstein's general relativity, which treats it as curved spacetime rather than a force mediated by particles. The other three forces are described by quantum field theories, where forces arise from particles exchanging force carrier particles, photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force. Attempts to create a quantum theory of gravity run into severe mathematical difficulties. When physicists try to apply quantum mechanics to general relativity, they get infinities, meaningless results that suggest something is wrong with the approach. Renormalization techniques that work beautifully for the other forces fail for gravity. One promising approach is string theory, which proposes that the fundamental constituents of reality aren't point particles, but tiny, vibrating strings. Different vibrational modes of these strings correspond to different particles. A string vibrating one way appears as an electron, vibrating another way appears as a quark, and so on. Importantly, string theory naturally includes a particle that behaves like the graviton, the hypothetical particle that would mediate gravity if it's a quantum force like the others. String theory is elegant and mathematically rich, but it has a problem. It requires extra dimensions of space. Not the 3 dimensions we experience, but 10 or 11 dimensions total. The extra dimensions would have to be compactified, curled up so small we can't detect them. Different ways of compactifying these dimensions lead to different physics in our observable 3-dimensional world. This leads to a vast landscape of possible universes, perhaps 10 to the power of 500 different possibilities. Critics argue this makes string theory unfalsifiable. If it predicts everything, it predicts nothing. Proponents argue we're still developing the mathematics and that testable predictions will emerge. For now, string theory remains a work in progress, tantalizingly beautiful, but not yet confirmed by experiment. Another approach is loop quantum gravity, which attempts to quantize spacetime itself, treating it as composed of discrete loops rather than a smooth continuum. This approach doesn't require extra dimensions and makes different predictions than string theory about the structure of spacetime at the smallest scales, the Planck scale, about 10 to the power of -35 meters. At the Planck scale, both quantum effects and gravitational effects become strong. Space and time might not be continuous, but granular, made of discrete units. The smooth spacetime of general relativity would be an approximation, valid at larger scales. Much like a smooth-looking beach is actually made of individual grains of sand. Testing these ideas is extraordinarily difficult. The Planck scale is far beyond the reach of any conceivable particle accelerator. To probe these energies directly, we'd need an accelerator the size of a galaxy. Instead, physicists look for indirect evidence, effects on light from distant cosmic events, signatures in gravitational waves, anomalies in the cosmic microwave background, radiation. Some physicists wonder if unification is even necessary. Perhaps the 4 forces are truly distinct, not manifestations of a single underlying force. Perhaps the universe is simply this way, with 4 independent forces that happen to coexist and create the complexity we observe. Not every question has to have a simpler answer lurking beneath. Others point out that even if we achieved a theory of everything, a single equation or framework describing all 4 forces, we'd still be left with questions. Why does that equation have the form it does? Why those particular constants and symmetries? A theory of everything would still rest on assumptions, on mathematical structures taken as given. The quest for deeper understanding might never truly end, but the search continues because unification has proven fruitful before. Maxwell's unification led to radio, television, radar, and countless other technologies. The electroweak unification deepened our understanding of particle physics and cosmology. Even if a final theory remains elusive, the journey toward it reveals profound truths about reality. Right now, experiments are searching for physics beyond the standard model. The Large Hadron Collider looks for new particles that might reveal deeper symmetries. Detectors deep underground watch for dark matter particles and rare decay processes. Astronomers study the cosmic microwave background and gravitational waves for clues about the universe's earliest moments. One intriguing possibility is supersymmetry, a proposed symmetry between matter particles and force particles. In supersymmetric theories, every known particle has a superpartner with different properties. These superpartners might make up dark matter. They might help unify the forces at high energies. They might solve certain mathematical problems in particle physics. But despite extensive searches, no superpartners have been found yet. Nature might not be supersymmetric, or the superpartners might be too heavy for our current accelerators to produce. The quest for unification is also a quest to understand the beginning. If all forces were unified in the first moments after the Big Bang, understanding that unified state would tell us about the origin of everything. It would reveal why the universe began with the particular forces and particles it has, why those forces separated in the way they did, and perhaps even why there's a universe at all rather than nothing. Some theories suggest our universe is just one bubble in an eternal inflating multiverse where different bubbles have different force strengths, different particles, different laws. We exist in this bubble because its forces happen to allow complex structures and life to form. In another bubble, perhaps gravity is stronger and stars collapse immediately into black holes. In another, perhaps the strong force is weaker and nuclei can't form. We observe this particular combination because it's compatible with our existence, a principle called the anthropic principle. Whether you find the anthropic principle satisfying or frustrating depends on your philosophical inclinations. It's scientifically testable in principle. If we ever found evidence of other universes with different laws, it would support the multiverse idea. But such evidence might be impossible to obtain. We might be limited to observing only our own bubble, leaving us wondering about all the others. Let's take a moment here and breathe. The quest for unification is both a scientific program and a deeply human impulse. We want to understand, to find patterns, to see connections. We want to know if the universe follows simple, elegant rules, or if it's irreducibly complex. We want to know if we're close to understanding everything, or if we're still missing something fundamental. The journey through unification theories can feel abstract, mathematical, far from everyday experience. But remember, the forces we're trying to unify are the same forces shaping your life right now. They're the reason you exist, the reason stars shine, the reason atoms bond, the reason you can think and wonder and rest peacefully in the darkness. Now, let's shift our perspective and consider what all of this means. How do the four forces, working together, create the universe we observe? What does their delicate balance tell us about the nature of reality? Let's explore the cosmic dance, the way these forces interplay to create everything from galaxies to thoughts. The universe exists in a state of remarkable balance. The four fundamental forces are precisely calibrated to allow complexity to emerge. Change any of them even slightly, and the universe would be unrecognizable, or perhaps wouldn't exist at all. This fine-tuning is one of the deepest puzzles in physics and cosmology. Consider gravity. If it were slightly stronger, stars would burn hotter and faster, exhausting their fuel in millions rather than billions of years. Planets might be pulled into their suns. Life which requires billions of years to evolve, would never have the chance. If gravity were weaker, stars might never ignite, or galaxies might never form. Matter would drift apart into a thin, cold fog. Or think about the strong force. If it were slightly weaker, atomic nuclei beyond hydrogen would be unstable. There would be no carbon, no oxygen, no complex chemistry. If it were stronger, protons might bind together directly, bypassing hydrogen. Stellar evolution would be different, perhaps preventing the formation of the diverse elements that life requires. The weak force, too, must be precisely what it is. If it were much stronger, the Big Bang would have converted more hydrogen into helium, leaving less hydrogen for later star formation. If it were much weaker, neutrons might not decay, or fusion in stars might proceed too quickly, destabilizing them. Even the electromagnetic force must fall within narrow bounds. If it were stronger, atoms would be smaller, and chemical reactions would require more energy. If it were weaker, atoms would be larger and less stable. The delicate chemistry of life depends on electromagnetic forces having roughly the strength they do. These aren't just hypothetical considerations. Physicists have calculated how the universe would change if the forces had different strengths. The conclusion is startling. Only a narrow range of force strengths permit the existence of complex structures, let alone life. We inhabit a universe that seems remarkably well suited to producing complexity. This fine-tuning problem has several possible explanations. Perhaps there's a deeper theory that explains why the forces must have these particular strengths, some mathematical necessity we haven't yet discovered. Perhaps there are many universes with different force strengths, and we necessarily find ourselves in one where the forces permit our existence. Perhaps it's just coincidence, though the odds against that seem astronomical. Or perhaps we're asking the wrong question. Maybe the forces aren't fine-tuned. Maybe complexity is more robust than we think, capable of emerging under a wider range of conditions than our models suggest. Maybe we suffer from a failure of imagination, unable to conceive of how different kinds of complexity might arise with different force strengths. Regardless of the explanation, the fact remains: the four forces work together in extraordinary harmony. Gravity gathers matter into stars and galaxies. The strong force allows stars to shine through fusion. Electromagnetism creates chemistry and structure. The weak force transforms particles, enabling fusion and creating the matter-antimatter asymmetry that left some matter for stars and people to be made from. In the early universe, these forces shaped cosmic evolution. In the first moments after the Big Bang, temperatures and energies were so extreme that the forces might have been unified. As the universe expanded and cooled, they separated, each taking on its distinct character. Within the first microsecond, quarks and gluons formed protons and neutrons through the strong force. Within the first few minutes, those protons and neutrons fused into light nuclei, mostly hydrogen and helium. For hundreds of thousands of years, the universe was too hot for atoms to form stably. Electrons and nuclei existed separately in a hot plasma. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons and nuclei to combine through electromagnetic attraction, forming stable atoms. This moment, called recombination, released light that's been traveling through space ever since. Light we now detect as the cosmic microwave background radiation, a faint glow filling the entire sky. With atoms formed, gravity could begin its patient work. Tiny density variations in the primordial gas, tiny fluctuations from quantum processes in the early universe, served as seeds. Gravity amplified these seeds, pulling more matter into denser regions. Over hundreds of millions of years, these regions collapsed into the first stars and galaxies. Inside those first stars, fusion began, the strong force overcoming electromagnetic repulsion in stellar cores, binding light elements into heavier ones. The weak force controlled the rate of fusion, ensuring stars burned slowly enough to live for millions or billions of years. When massive stars exhausted their fuel, they exploded as supernovae, scattering heavy elements into space. These elements, carbon, nitrogen, oxygen, iron, and dozens of others, were incorporated into later generations of stars and planets. Our solar system formed from such enriched material about 4.6 billion years ago. The Earth coalesced from rocky debris, its gravity holding it together, its electromagnetic properties determining which materials bonded into rocks and minerals. On Earth's surface, chemistry began to explore new possibilities. Molecules formed, broke apart, reformed in new combinations. Electromagnetic forces guided every interaction, creating increasingly complex structures. Somewhere in this process, perhaps in warm tidal pools or deep-sea vents, chemistry crossed a threshold and became biochemistry. Life emerged. Living things are intricate dances of the four forces. Gravity keeps us on the ground and shapes our body structures. Bones and muscles evolved to work with Earth's gravitational field. Electromagnetism drives all the chemistry of life: DNA, proteins, metabolism, nervous signals. The strong force holds stable the atomic nuclei we're made of. The weak force governs radioactive decays that contribute to Earth's internal heat, driving plate tectonics and creating the geological diversity that may have fostered life's origin. You are, in every sense, a product of all four forces working in concert. The calcium in your bones came from stars where the strong force forged light elements into heavier ones. The electrical signals in your brain are electromagnetic. Your mass, your weight, your relationship to the ground beneath you, gravity. The slow transformations of radioactive elements in your body, the weak force. The forces don't just coexist, they interplay. Stars form through gravity, but they shine through the strong force, and their light, electromagnetic radiation, carries energy across space. That energy drives photosynthesis on Earth, storing electromagnetic energy in chemical bonds, which animals then release to power their bodies. The cycle connects all four forces in an elegant flow. Even consciousness might emerge from this interplay. Your thoughts arise from electromagnetic signals cascading through neural networks whose structures were shaped by chemistry, which depends on electromagnetic forces in a brain held together by gravity, made of atoms bound by the strong force, in a body sustained by metabolic processes powered ultimately by stellar fusion. The universe doesn't need to be this way. There's no logical necessity for four forces with these particular properties. Yet here we are, in a cosmos where these forces exist and balance perfectly to create stars, planets, chemistry, life, and minds capable of wondering why. Some see this as evidence of design, a cosmic intention behind the fine-tuning. Others see it as selection bias. Of course, we find ourselves in a universe compatible with our existence. We couldn't exist in any other kind. Still, others simply marvel at the improbability, acknowledging the mystery without insisting on any particular explanation. Let's pause and breathe here. The cosmic balance is both fragile and robust. Fragile because small changes would make the universe unrecognizable. Robust because once established, these forces create a stable framework for billions of years of evolution and emergence. The universe is old enough for galaxies to form, stars to live and die multiple generations, and for complex chemistry to explore vast reaches of possibility space. Right now, in this moment, the forces are at work everywhere. Gravity is pulling galaxies together across millions of light years. Electromagnetic radiation is streaming from stars, carrying information about their composition and motion. The strong force is binding nuclei in every atom of every star, planet, and living thing. The weak force is transforming particles in stellar cores and radioactive decay chains. This simultaneous distributed activity creates a universe that's dynamic, interesting, and generative. Things happen. Stars are born and die. Planets form and evolve. Chemistry explores new combinations. Life emerges, evolves, and perhaps wonders about its origins. All of this flows from four simple forces operating according to mathematical laws. The harmony of the forces is perhaps most evident in the elements themselves. Each element's properties arise from the interplay of all four forces. Hydrogen is simple: one proton, one electron, bound electromagnetically. But that proton is held together by the strong force, and its stability depends on the balance between strong and electromagnetic interactions. Heavier elements require more delicate balances, more protons repelling electromagnetically, more nucleons bound by the strong force, often neutrons transformed from or into protons via the weak force. The periodic table is a map of this balance, showing which combinations of protons and neutrons are stable, which are not, and how elements relate to each other chemically. Every entry in the periodic table represents a successful balance of forces, a configuration where the strong force wins over electromagnetic repulsion, where electrons arrange themselves in stable shells, where the nucleus neither flies apart nor collapses. Life depends on this balance, producing a wide variety of stable elements. Carbon, with 6 protons, forms the backbone of organic molecules because its electromagnetic properties allow it to bond in diverse ways. Oxygen's eagerness to attract electrons makes it perfect for energy-releasing reactions. Iron's properties make it ideal for carrying oxygen in blood. Each element's biological role stems from how the forces shaped its properties. Even the rarity of certain elements tells a story. Gold is rare because it requires specific conditions to form, probably neutron-star collisions. The forces that make gold atoms possible also ensure they're difficult to create, requiring extreme energies and specific nuclear reactions. Gold's chemical stability, its resistance to corrosion, comes from how tightly electromagnetism binds its electrons. Gold is valuable partly because the forces conspired to make it both beautiful and scarce. The forces even determine what's possible in terms of technology and civilization. We can build structures because gravity is weak enough not to crush them, but strong enough to hold materials together. We can manipulate materials through chemistry because electromagnetic forces are strong enough to matter, but not so strong that we can't break bonds with moderate energy. We can harness nuclear energy because the strong force stores tremendous energy in nuclei that can be released under certain conditions. In a universe with different force strengths, technology might be impossible or might take completely different forms. Perhaps civilizations in other hypothetical universes face different challenges, exploit different physics, build with different materials. Or perhaps no civilizations arise at all because the forces don't permit the complexity required for life. Our universe, with its particular balance of forces, is one where complexity can accumulate. Simple hydrogen can become helium. Helium and hydrogen can become carbon and oxygen. These can combine into water, carbon dioxide, sugars, amino acids. Amino acids can become proteins. Proteins can catalyze reactions that make more proteins. Eventually, this chemical recursion becomes life, and life becomes consciousness, and consciousness looks back on the process with wonder. The forces don't plan this. They don't have intentions or goals. They simply operate according to their natures, and the cumulative effect of their operations over billions of years is the universe we inhabit. Its emergence all the way up. Simple rules producing complex phenomena, producing more complex phenomena, with each level building on the previous. You might think this makes existence cold or meaningless, just blind forces grinding away. But actually, it makes existence more remarkable. Meaning, beauty, consciousness. These emerge spontaneously from the interplay of 4 fundamental forces. They weren't programmed in from the start. They arose naturally as the universe explored possibilities, as matter and energy found new ways to organize themselves. The balance is also dynamic. Forces oppose and complement each other constantly. Gravity tries to crush stars. Internal pressure from fusion resists. Electromagnetic repulsion tries to blow nuclei apart. The strong force holds them together. The weak force transforms particles. Other forces determine what transformations are possible. It's a constant negotiation, a cosmic dance where partners push and pull, creating motion and structure through their interaction. This dynamic balance extends across all scales. In atoms, electromagnetic attraction and quantum mechanics determine electron shells. In molecules, electromagnetic forces create bonds that can be broken and reformed. In living cells, chemistry is carefully controlled, energy is harvested and spent, information is stored and read. In organisms, gravity shapes bodies, chemistry powers metabolism, physics constrains what's possible. In planets and stars, gravity compresses, fusion generates energy, chemistry determines composition. In galaxies, gravity and motion balance to create stable structures. At every scale, the forces are present, interacting, creating the possibility space within which reality unfolds. Change any force, and the entire tower of emergence changes. Weaken gravity, and stars become different. Which changes which elements form. Which changes chemistry. Which changes biology. Which changes everything. The universe is an integrated whole, not a collection of independent pieces. The forces that operate in distant galaxies are the same forces operating in your body. The physics that governs cosmic evolution governs cellular metabolism. The laws that determine stellar fusion determine chemical bonding. There's a unity to nature, even if we haven't yet found the theory that perfectly expresses it. Let's take a breath here and consider what we've explored. 4 forces, each with distinct properties, operating according to mathematical laws, interacting in ways that permit, perhaps require the universe to be interesting, complex, and generative. It's not the only possible universe, but it's the one we inhabit, and understanding its balance helps us appreciate how remarkable our existence truly is. Now let's turn our attention to the human story embedded in all of this. How did we come to understand these forces? What did the discovery process reveal about both nature and ourselves? Let's explore the history of physics as a story of gradually uncovering the hidden architecture of reality. For most of human history, we knew nothing about fundamental forces. Ancient peoples observed the world, saw patterns, created explanations. Things fell downward. Perhaps they sought their natural place. Magnets attracted iron. Perhaps they contained spirits or were drawn by sympathy. Fire rose upward. Perhaps it belonged to the celestial realm. The explanations were poetic, intuitive, often wrong, but they represented humanity's first attempts to understand nature's regularities. The scientific revolution changed everything. Galileo Galilei, in the late 1500s and early 1600s, began asking different questions. Not why in the teleological sense, but how in the mathematical sense. How fast do objects fall? How do projectiles move? How can we describe motion precisely? His approach, careful observation, measurement, mathematical description, created the template for modern physics. Isaac Newton, building on Galileo's work, formulated the laws of motion and universal gravitation. His 1687 masterwork, Philosophia Naturalis Principia Mathematica, changed how we understood the universe. Suddenly, the same laws that governed falling apples governed planetary orbits. Heaven and earth followed the same rules. The universe was comprehensible, predictable, mathematical. Newton's work was revolutionary, but he was troubled by one aspect of his theory. Gravity seemed to act instantaneously across empty space, with no mechanism. How did the Earth know about the Sun's presence millions of kilometers away? Newton himself wrote that he framed no hypotheses about this. He simply described how gravity worked, not what it was. For 2 centuries, Newton's laws reigned supreme. Then came unexpected observations. Mercury's orbit didn't quite match predictions. Light was bent by gravity during solar eclipses. Clocks ran at different rates depending on altitude and motion. Something was wrong, or rather, something was incomplete, about Newtonian gravity. Albert Einstein, working as a patent clerk in Switzerland, thought deeply about space, time, and motion. His 1905 special theory of relativity showed that space and time were intertwined, that simultaneity was relative, that nothing could travel faster than light. Then, over the next decade, he extended these ideas to accelerated motion and gravity, producing general relativity in 1915. Einstein's picture of gravity as curved spacetime was radical. It solved the problems with Mercury's orbit and predicted new phenomena like gravitational lensing and gravitational waves. But it also created new puzzles. How could we reconcile curved spacetime with the quantum nature of matter? This question still haunts physics today. While Newton and Einstein were revealing gravity's nature, others were uncovering electromagnetism. In the early 1800s, scientists like Alessandro Volta, Hans Christian Ørsted, Michael Faraday, and Joseph Henry conducted careful experiments with electricity and magnetism. They discovered that electric currents create magnetic fields, that changing magnetic fields induce electric currents, that electricity and magnetism were deeply connected. James Clerk Maxwell synthesized these discoveries into 4 elegant equations in the 1860s. Maxwell's equations revealed that light was an electromagnetic wave, that electricity and magnetism were unified, that invisible fields permeated all of space. His work stands among the greatest intellectual achievements in human history, comparable to Newton's laws or Einstein's relativity. The discovery of atomic structure brought new mysteries. By the early 1900s, it was clear atoms had nuclei containing positive charges. But how could multiple positive charges coexist in such a tiny space? They should repel each other with enormous force. Something must be holding nuclei together. This something was the strong nuclear force, though decades passed before physicists fully understood it. In the 1930s and 1940s, researchers realized a new force must exist, one that only operated at nuclear distances but was powerful enough to overcome electromagnetic repulsion. They called it the strong force and gradually worked out its properties. The weak force was discovered through observations of radioactive beta decay. In the late 1800s and early 1900s, scientists noticed certain elements emitted electrons spontaneously. The nucleus seemed to be transforming itself, changing one element into another. This violated everything known about chemistry and physics at the time. Wolfgang Pauli's 1930 proposal of the neutrino, an invisible, nearly massless particle, helped solve the puzzle. Beta decay was a weak force process where a neutron transformed into a proton, electron, and antineutrino. But confirming this took decades. Neutrinos interact so weakly with matter that detecting them seemed almost impossible. In 1956, Frederick Rains and Clyde Cowan finally detected neutrinos coming from a nuclear reactor. They had to place their detector deep underground, shielded from cosmic rays, next to a powerful reactor producing trillions of neutrinos per second. Even then, they detected only a handful of interactions. The weak force was finally confirmed experimentally. The unification of electromagnetism and the weak force in the 1960s and 1970s was a triumph of theoretical physics. Glashow, Salam, and Weinberg showed these forces were unified at high energies, separated only by spontaneous symmetry breaking at lower energies. The discovery of the W and Z bosons in 1983 confirmed their theory, as did the discovery of the Higgs boson in 2012. Understanding the strong force required developing quantum chromodynamics in the 1970s. Physicists realized protons and neutrons weren't fundamental. They were made of quarks bound by gluons. The mathematics was complex, the predictions difficult to calculate, but experiment after experiment confirmed QCD's validity. These discoveries weren't made by isolated geniuses working alone. They emerged from communities of scientists sharing ideas, building on each other's work, arguing, collaborating, competing. Newton famously wrote that he stood on the shoulders of giants. All scientists do. Knowledge accumulates gradually, with occasional revolutionary insights that reframe everything. The tools of discovery also evolved. Early physicists had crude instruments, pendulums, inclined planes, simple electrical apparatus. Modern physics requires particle accelerators kilometers in circumference, detectors weighing thousands of tons, collaborations of thousands of researchers from dozens of countries. The Large Hadron Collider at CERN cost billions of dollars and took decades to build. Yet the fundamental approach remains similar. Observe nature carefully, notice patterns and anomalies, develop mathematical theories to explain what you observe. Make predictions. Test those predictions through new observations or experiments. Refine or discard theories based on results. The scientific method, refined over centuries, is how we've gradually unveiled the invisible architecture of reality. This process isn't finished. We still don't know what dark matter is, despite knowing it dominates the gravitational landscape. We don't know what dark energy is, despite knowing its accelerating cosmic expansion. We haven't unified gravity with the other forces. We don't fully understand why the forces have the strengths they do, or why there are 4 forces rather than 3 or 5 or 1. Every answer raises new questions. That's not a failure of science. It's its greatest strength. Each discovery reveals new horizons, new mysteries, new territories to explore. The more we learn, the more we realize how much remains unknown. The universe is far richer and stranger than anyone imagined. Future discoveries might revolutionize physics again. Perhaps we'll detect gravitational waves with such precision we can observe quantum properties of space-time. Perhaps we'll find supersymmetric particles or extra dimensions. Perhaps we'll discover the weak force-violated CP symmetry in ways we haven't yet measured, revealing new physics. Perhaps some teenager in a school somewhere will have an insight that opens entirely new perspectives. Or perhaps the universe will keep its deepest secrets. Perhaps some questions are beyond our capacity to answer, not because we lack intelligence, but because we lack the right concepts, or because the universe simply doesn't make those answers accessible. Recognizing the limits of knowledge is itself a kind of wisdom. But within those limits, we've accomplished something extraordinary. We've uncovered 4 fundamental forces. We've described them mathematically. We've tested our descriptions to incredible precision. We've used this knowledge to build technologies that would seem like magic to our ancestors. We've learned to ask better questions about existence itself. The story of discovering the forces is also the story of human curiosity, persistence, and ingenuity. It's thousands of people across centuries, each contributing a small piece to the puzzle, gradually revealing a picture of stunning beauty and complexity. It's one of humanity's great collective achievements, comparable to art, literature, or philosophy, perhaps exceeding them in scope and impact. Right now, researchers around the world are conducting experiments, analyzing data, developing theories. They're searching for phenomena beyond the standard model. They're mapping the cosmos with ever greater precision. They're probing the quantum realm for new physics. Each contributes to the ongoing project of understanding reality. You might think this is all abstract, relevant only to specialists. But the forces these researchers study are the same forces shaping your existence. Understanding them deepens appreciation for how remarkable it is that anything exists, that you exist, that the universe conspired across billions of years to create the conditions for consciousness to emerge and wonder about its origins. Let's pause here and take a breath. The discovery of the forces is an ongoing story, not finished, perhaps never finished. But already we've learned enough to know that reality operates according to elegant mathematical principles, that the universe is comprehensible, and that understanding it enriches human existence in profound ways. Now, as we move toward the end of our journey, let's consider what all of this means. What does understanding the 4 forces tell us about existence, meaning, and our place in the cosmos? Let's explore the philosophical implications of our scientific knowledge. Understanding the 4 fundamental forces raises profound questions. If everything reduces to particles interacting through these forces, what does that mean for concepts like free will, consciousness, beauty, or meaning? If the universe operates according to mathematical laws, Is everything predetermined? If we're just matter and energy following physical rules, where does meaning come from? These are ancient questions, debated by philosophers long before modern physics. But our understanding of the forces provides new context, new constraints on possible answers. We can't ignore what physics tells us about reality when considering these questions. Start with determinism. If the forces follow mathematical laws, and if the state of the universe at one moment determines its state at the next, then isn't everything predetermined from the Big Bang onward? Are we just watching a movie that's already filmed, with no genuine freedom or choice? Classical physics suggested yes, Newton's laws were deterministic. Given precise initial conditions, you could calculate the future perfectly. The universe was like an enormous clockwork mechanism, wound up at the beginning and ticking along according to fixed rules. This troubled some people, comforted others. But quantum mechanics introduced fundamental uncertainty. At the quantum level, outcomes are probabilistic, not deterministic. You can't predict exactly when a particular radioactive nucleus will decay, only the probability distribution. You can't simultaneously know a particle's position and momentum with perfect precision. There's inherent randomness built into reality at the most fundamental level. Does quantum indeterminacy provide room for free will? Not obviously. Random quantum events don't seem like freedom. They're just randomness. Free will, if it exists, would need to be something more than particles following laws plus random quantum fluctuations. Perhaps there are emergent properties of complex systems that genuinely create new causal powers. Perhaps consciousness involves processes we don't yet understand. Or perhaps free will is an illusion, though a persistent and useful one. There's no consensus among philosophers or scientists. Some argue determinism is true, but compatible with meaningful freedom. Others argue quantum mechanics leaves room for genuine indeterminacy. Still, others suggest the question itself is confused, that free will doesn't refer to anything coherent. The forces don't resolve this debate, they simply constrain it, ruling out certain possibilities while leaving others open. What about consciousness? You are aware. You experience sensations, emotions, thoughts. You have a subjective inner life. How does this emerge from particles interacting through electromagnetic and other forces? This is the hard problem of consciousness, and it's genuinely hard. We can explain neural mechanisms, how signals propagate, how information is processed, but explaining why these processes are accompanied by subjective experience, why there's something it's like to be you, remains mysterious. Some philosophers argue consciousness is fundamental, not reducible to physical processes. Others argue it's an emergent property of complex information processing. Still others suggest the problem stems from confused concepts about what consciousness is. The forces don't directly answer this question, but they do establish that whatever consciousness is, it must be compatible with physical law. Your thoughts right now involve electromagnetic signals in your brain. The atoms those signals flow through are held together by the strong force and bound into molecules by electromagnetic forces. Your brain is made of matter that formed in stars through nuclear processes. There's a continuous chain connecting your conscious experience to the fundamental forces, even if we don't fully understand all the links. Perhaps consciousness is what certain patterns of force interactions feel like from the inside. Perhaps experience is an intrinsic aspect of information processing above certain thresholds of complexity. Perhaps there are aspects of reality we're missing, properties beyond the forces we've discovered. The question remains open, inviting exploration rather than foreclosing it. What about meaning and purpose? If the universe is just particles following physical laws, does anything matter? The forces don't seem to care about human concerns. Gravity doesn't distinguish between pulling on a person or a rock. Electromagnetism doesn't value beauty or goodness. The universe operates indifferently, without reference to human values. Yet meaning exists. You care about things. Beauty moves you. Relationships matter. Suffering is bad. Joy is good. These aren't illusions. They're genuine features of your experience, perhaps the most fundamental features. How do we reconcile the apparent meaninglessness of physics with the undeniable meaningfulness of life? One approach is to recognize that meaning emerges at higher levels of organization. Molecules don't have purposes, but organisms do. Particles don't have values, but conscious beings do. The forces enable complexity, and complexity enables meaning. There's no contradiction between underlying physical processes and emergent significance. Another approach emphasizes that we create meaning. The universe doesn't provide purpose from outside. We generate it from within. This makes meaning no less real. Human values and concerns are part of reality, arising naturally from how consciousness and society work. That they emerge from physical processes doesn't diminish them. A third approach suggests we don't yet understand enough. Perhaps meaning is more fundamental than we realize, woven into reality in ways our current physics doesn't capture. Perhaps consciousness connects to deeper levels of existence. Perhaps the mathematical laws themselves reflect something purposeful, though what that might be remains mysterious. The forces also raise questions about why this universe exists rather than nothing. Why are there four forces with these particular strengths? Why do they permit complexity and life? Why is there anything at all rather than absolute emptiness? Physics can't answer why these laws exist. It can only describe what they are and how they work. Perhaps there's no why, just is. Perhaps the universe is a brute fact, requiring no explanation. Perhaps existence is necessary in some sense we don't understand. Perhaps our universe is one bubble in an infinite multiverse, and we observe this particular set of forces because only such forces permit observers. These questions touch on metaphysics, the branch of philosophy concerned with the nature of reality itself. Science and philosophy overlap here, both trying to make sense of existence. The forces provide crucial data points, constraints on theorizing, but they don't determine final answers. There's also beauty to consider. Many physicists report finding deep aesthetic satisfaction in the equations describing the forces. Maxwell's equations are elegant. Einstein's field equations are beautiful. The Standard Model, for all its complexity, reveals patterns and symmetries that seem almost too perfect to be coincidental. Is this beauty inherent in nature, or is it projected by minds seeking patterns? Perhaps both. Perhaps our minds evolved to recognize certain mathematical structures as beautiful because those structures reflect deep truths about reality. Perhaps beauty is how understanding feels, the pleasure of seeing connections and patterns. The forces also reveal a universe that's comprehensible. Reality follows rules we can discover, express mathematically, test experimentally. This is remarkable and not obviously necessary. The universe could have been chaotic, patternless, incomprehensible. That it's not. That mathematics invented by humans describes physical reality, suggests a deep harmony between mind and nature. Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract mathematical structures correspond so precisely to physical phenomena? Why should equations written on paper predict experimental outcomes? It's almost spooky, yet it works consistently. Perhaps mathematics is discovered, not invented. We're finding structures that exist independently of us. Perhaps mathematics is the language the universe speaks, and we're learning to read it. Or perhaps our mathematics reflects patterns in how we think, and those patterns match physical patterns because we evolved in a physical universe. The relationship between mathematics and physics remains philosophically puzzling, despite being practically powerful. Understanding the forces also changes how we see ourselves. We're not separate from nature, looking in from outside. We're part of it, made of atoms that obey the same forces as stars and stones. There's no fundamental distinction between living and non-living matter, just different levels of organization, different patterns of complexity. This can feel reductive, as if we're nothing but atoms. But actually, It's ennobling. You're continuous with the cosmos. The forces shaping galaxies shape you. The processes that formed elements in stars created your body. You're not apart from the universe. You're one way the universe organizes itself, becomes aware of itself, wonders about itself. Carl Sagan beautifully expressed this. We are a way for the cosmos to know itself. Your curiosity about the forces is the universe studying itself through you. Your appreciation of beauty is matter and energy learning to value its own patterns. Your search for meaning is existence becoming conscious of its own significance. This perspective doesn't eliminate mystery, it deepens it. How remarkable that the universe became complex enough to generate consciousness. How extraordinary that particles following simple forces created systems capable of understanding those forces. The more we learn, the more profound the mystery of existence becomes. Some find this perspective comforting, connecting them to something larger than themselves. Others find it cold or diminishing. There's no single correct emotional response. The forces themselves are neutral, but what we make of them, how we integrate this knowledge into our worldview, varies from person to person. Let's breathe here for a moment. The philosophical implications of understanding the forces are vast, touching on free will, consciousness, meaning, beauty, existence itself. These aren't settled questions with clear answers. They're ongoing inquiries where science and philosophy intersect, where knowledge meets wonder, where understanding generates new mysteries rather than eliminating them. As we approach the end of our journey, let's consider one final perspective. The deeply personal meaning of these forces, not philosophically or scientifically, but intimately, in terms of your own existence right now. How do the forces shape your life? What does it mean that you're a being created by and subject to these four fundamental interactions? Right now, as you lie there in whatever state of sleepiness or wakefulness you find yourself, all four forces are intimately involved in your existence. Let's make this concrete, bringing the abstract down to the immediate, the personal, the bodily reality of your present moment. Start with gravity. Feel it. Feel the weight of your body against whatever surface supports you. That sensation, that gentle but persistent pressure, is gravity acting on your mass, pulling you toward Earth's center. Every cell in your body experiences this pull. Your blood pulls slightly toward your lower side. Your organs rest against each other. Your spine compresses ever so slightly. Gravity has shaped your body throughout your life. As a baby, you learn to lift your head against it, to sit up, to stand, to walk. Your muscles developed in response to gravitational resistance. Your bones grew dense enough to support your weight. Your heart evolved to pump blood upward against gravity's pull. Remove gravity, and your body would slowly weaken. Bones would lose density, muscles would atrophy, your cardiovascular system would struggle when you return to Earth. Every time you've ever stood up, lifted something, climbed stairs, or jumped, you've worked against gravity. Every time you've lain down, you've surrendered to it. It's so constant you rarely notice it, yet it's shaping your posture right now, determining how blood flows through your body, influencing your sense of orientation and balance. Now consider electromagnetism. It's everywhere in your experience, though invisible. The light you see, whether from screens, lamps, or memory of daylight, is electromagnetic radiation hitting your retina and triggering cascades of electrical signals. Those signals travel via electromagnetic processes through your optic nerves to your visual cortex, where they're somehow transformed into the experience of seeing. Every sensation you feel is electromagnetic. Touch receptors in your skin respond to pressure by generating electrical signals. Temperature receptors measure thermal energy, the vibration of molecules, an electromagnetic phenomenon. Pain receptors fire electrical warnings when tissue is damaged. Your entire sensory experience of the world is mediated by electromagnetic forces. Your thoughts are electromagnetic. Right now, As you process these words, ions are flowing across neural membranes, creating electrical potentials that propagate through networks of neurons. Neurotransmitters, molecules held together by electromagnetic bonds, cross synapses, triggering more electrical signals. The physical substrate of consciousness is electromagnetic activity in neural tissue. Even your emotions have electromagnetic signatures. When you're anxious, your heart rate increases, driven by electrical signals from your nervous system. When you're calm, your breathing slows, regulated by neural signals that are fundamentally electromagnetic. Your subjective inner life correlates with objective electromagnetic activity in your body. The solidity of your body is electromagnetic. You feel solid, bounded, separate from your surroundings. But this is electromagnetic repulsion. The electrons in your skin repel the electrons in anything you touch. You've never truly touched anything. You're always hovering a tiny distance away, held back by electromagnetic forces. The sensation of touch is electromagnetic interaction at a distance measured in nanometers. The strong force is less directly perceptible, but no less essential. Every nucleus in every atom of your body is held together by the strong force. Without it, you would instantly dissolve into a cloud of protons and electrons. No atoms, no molecules, no body. The strong force operates at scales far too small to see or feel, yet it's the foundation of material existence. The atoms in your body were created through strong force processes. Carbon atoms formed in stars when 3 helium nuclei fused together. Strong force interactions in stellar furnaces. Oxygen formed when helium fused with carbon. Nitrogen, calcium, iron, all forged in stars through nuclear processes governed by the strong force. You are literally star stuff, held together by nuclear glue. The energy you're using right now, whether actively thinking or drifting towards sleep, ultimately comes from fusion in the sun. Sunlight hit plants or plankton, driving photosynthesis. You ate those plants, or ate animals that ate plants. Your cells broke down those molecules, releasing energy originally stored by electromagnetic interactions, but ultimately sourced from solar fusion. Strong force processes. The weak force is the subtlest but still present. Radioactive isotopes in your body, carbon-14, potassium-40, and others, undergo beta decay through weak interactions. The rate is slow, the effects minimal, but they're happening constantly. About 5,000 atoms in your body decay every second through weak force processes. These contribute a small fraction of your background radiation dose. The weak force also shaped the matter you're made of. In the early universe, weak interactions determined the ratio of protons to neutrons, influencing which elements could form. The fact that protons are stable, they don't decay on human timescales, is partly due to weak force properties. If the weak force was slightly different, the early universe might have produced a very different mix of elements, perhaps incompatible with life. So here you are, a temporary configuration of matter and energy, held together by 4 forces, shaped by billions of years of cosmic evolution, experiencing a moment of consciousness that is itself an electromagnetic process, arising from complex structures made possible by all 4 forces working in concert. Your existence is improbable. The forces had to have exactly the strengths they do. The early universe had to evolve in specific ways. Stars had to form, live, die, and scatter heavy elements. A particular planet had to form at the right distance from a star. Chemistry had to explore vast possibility spaces until it stumbled on self-replication. Evolution had to run for billions of years, navigating countless contingencies. Yet here you are, not inevitable, but actual. The universe, through its forces and their consequences, created the conditions for your existence. You're not separate from the cosmos, you're an expression of it. One-way matter and energy organize themselves, one instance of the universe becoming aware of itself. This can evoke different feelings. Some find it humbling, realizing how small and temporary we are in cosmic terms. Others find it empowering, recognizing that we're part of something vast and ancient. Still others feel a kind of grateful wonder that existence conspired to create consciousness, awareness, the capacity to understand and appreciate reality. There's no prescribed emotion you should feel. The forces themselves are neutral, indifferent to human concerns. But your response to understanding them, that's deeply personal, shaped by your history, your temperament, your current state of mind. And that's as it should be. We each integrate knowledge into our lives differently. Some people find that understanding the forces deepens their spiritual sense. They see elegance and beauty in physical law, interpret the fine-tuning as evidence of purpose or design, feel connected to something transcendent through scientific understanding. Physics doesn't contradict spirituality for them, it enriches it, providing deeper appreciation of creation or cosmos or existence. Others find that understanding the forces changes nothing fundamental in their daily experience. Life continues with its joys and challenges. Relationships remain meaningful. Work is still work. Pleasure is still pleasure. The forces are background context, intellectually interesting, but not transformative. And that's fine too. Not every insight needs to revolutionize your worldview. Still, others find that understanding the forces makes everyday experience richer. Looking at a sunrise becomes an appreciation of electromagnetic radiation, streaming from fusion processes 150 million kilometers away. Holding someone's hand becomes an awareness of electromagnetic repulsion, creating the sensation of touch. Walking becomes a negotiation with gravity. Each moment contains layers of meaning, immediate experience enriched by understanding. Your body is a temporary arrangement, a pattern that persists for decades but eventually dissolves. The forces that hold you together will continue after you're gone, arranging matter and energy into new configurations. The atoms that currently constitute your body will disperse, joining soil, air, water, eventually incorporating into other organisms. The pattern, that is, you will cease, but the stuff you're made of continues its journey. This might sound morbid, but it needn't be. It's simply true, and truth has its own beauty. You're a brief local organization of complexity in a universe that tends toward entropy overall. The forces created the conditions for your existence and will persist long after. Being temporary doesn't make you meaningless. If anything, it makes each moment more precious. Right now, you're alive, aware, experiencing. The forces are enabling this. Your neurons are firing, your heart is beating, your lungs are breathing. Electromagnetic processes carry information through your nervous system. Gravity keeps you grounded. The strong force holds your matter together. The weak force very slowly transforms some particles deep within you. It's all happening right now, this moment, as you rest there. You don't need to do anything with this knowledge. You don't need to have profound realizations or life-changing insights. It's enough to simply appreciate, quietly, that you understand a little more about why you exist, what you're made of, how the universe works. This understanding is part of being human, using our evolved capacity for abstract thought to comprehend the foundations of reality. The forces don't care whether you understand them. Stars would shine, atoms would bond, matter would interact regardless of human knowledge. But we do understand, at least partially, and that's remarkable. A universe that produces beings capable of understanding it is more interesting than one that doesn't. You're participating in cosmic self-awareness, the universe knowing itself through you. Let your body relax more deeply now. Feel gravity holding you gently. Sense the electromagnetic activity in your nervous system beginning to quiet as you approach sleep. Know that the strong force continues its tireless work, holding your atoms together. Accept that the weak force operates on timescales beyond your perception, slowly transforming particles according to its nature. You are held, supported, sustained by the four fundamental forces. They ask nothing of you. They simply operate, enabling your existence, making consciousness possible. And in this moment of understanding, you're connected to the deepest principles of reality, to the architecture that makes everything possible. As we drift toward our conclusion, carry this awareness lightly. The forces are always there, operating quietly, maintaining the possibility of existence. You don't need to think about them constantly, but knowing they're there, understanding them even a little, can add a dimension to experience, a sense of connection to something vast, ancient, elegant, and ongoing. Let's move now toward our final reflections, bringing this gentle journey through physics to a soft landing. We'll gather the threads we've explored, acknowledge what remains mysterious, and bid each other a peaceful farewell under the same forces that hold galaxies together and make your thoughts possible. We've traveled through the four fundamental forces, explored their properties, traced their effects from the quantum to the cosmic. Yet for all we've learned, profound mysteries remain. The universe hasn't given up all its secrets. Perhaps it never will. We don't know why there are four forces rather than 3 or 5 or 1. The number 4 seems arbitrary, not derived from any deeper principle we understand. Perhaps future theories will reveal why 4 is necessary or natural. Or perhaps it's simply how our universe happens to be, one possibility among many that could have existed. We don't know why the forces have the particular strengths they do. Why is gravity so much weaker than electromagnetism? Why is the strong force exactly strong enough to bind nuclei but not stronger? The values seem finely tuned, yet we don't understand where these values come from. Are they determined by some deeper mathematics? Or are they random initial conditions? Or something else entirely? We don't understand what happened in the first moments of the Big Bang. Our physics breaks down as we approach the initial singularity, the moment of infinite density and temperature. Quantum effects and gravitational effects both become extreme, yet we lack a theory that handles both simultaneously. The very beginning remains obscure, hidden behind a veil of mathematical breakdown. We don't know what dark matter is. It dominates the gravitational landscape, outweighing normal matter by 5 to 1, yet we've never detected a dark matter particle directly. We infer its existence from gravitational effects. Galaxies rotate too fast. Galaxy clusters contain more mass than we can see. Gravitational lensing reveals invisible matter. But what dark matter actually consists of remains mysterious. Is it a new particle, something beyond the standard model? Is it a modification to gravity at galactic scales? Is it primordial black holes formed in the early universe? Decades of searching have ruled out many possibilities, but haven't identified the answer. Dark matter remains one of the greatest unsolved problems in physics. Dark energy is even more mysterious. It makes up about 68% of the universe's total mass energy, yet we don't know what it is. It causes cosmic expansion to accelerate, opposing gravity on the largest scales. Einstein's cosmological constant, which he once called his greatest blunder, now seems necessary to explain observations. But what is the cosmological constant? Is it the energy of empty space itself, the vacuum bubbling with virtual particles? If so, why does it have the value it does? Naive quantum calculations predict it should be 120 orders of magnitude larger, the worst prediction in physics. Something profound is missing from our understanding. We don't have a quantum theory of gravity. General relativity describes gravity beautifully at large scales, but it's not a quantum theory. Quantum mechanics describes the other forces elegantly, but treats space-time as a fixed background. Reconciling these frameworks has proven extraordinarily difficult. String theory and loop quantum gravity are attempts, but neither is confirmed, and both remain works in progress. Without quantum gravity, we can't fully understand black holes. We can describe their external properties, mass, spin, charge, but not what happens at their centers, where quantum effects and gravitational effects both become extreme. We can't explain Hawking radiation fully, the theoretical process by which black holes slowly evaporate. The information paradox, what happens to information that falls into a black hole, remains unsolved. We don't understand the early universe's rapid expansion, called cosmic inflation. Observations suggest the universe expanded exponentially in the first tiny fraction of a second, smoothing out irregularities and setting initial conditions for later structure formation. But what drove inflation? What field or mechanism caused it? How did it start and stop? Various models exist, but none is confirmed. We don't know if our universe is unique. The multiverse hypothesis suggests countless universes exist, each perhaps with different force strengths, different particles, different laws. Our universe's apparent fine-tuning would then be selection bias. We observe this particular universe because it's compatible with our existence. But the multiverse hypothesis is controversial, potentially unfalsifiable, and far from established. We don't fully understand the arrow of time. The fundamental forces are mostly time-symmetric. They work equally well forward or backward in time. Yet our experience is strongly time-asymmetric. We remember the past, but not the future. Entropy increases over time. Causes precede effects. Why does time have a direction, and how does this emerge from time-symmetric laws? The second law of thermodynamics, entropy tends to increase, might explain the arrow of time. But why did the universe start in such a low entropy state? The Big Bang seems to have been remarkably organized, highly ordered, with entropy far below its maximum. This low initial entropy might be the ultimate reason time has an arrow. But we don't know why the universe began that way. We don't understand consciousness. How does subjective experience arise from electromagnetic signals in neural tissue? Why is there something it's like to be you? The hard problem of consciousness remains hard, despite progress in neuroscience and cognitive science. Understanding the forces doesn't automatically explain how they produce awareness. Perhaps consciousness is an emergent property of sufficient complexity. Perhaps it requires quantum effects in microtubules or other cellular structures. Perhaps it's more fundamental than we realize, a basic feature of reality like mass or charge. Or perhaps the question itself is confused, based on flawed assumptions about what consciousness is. We simply don't know. We don't know if we'll ever find a theory of everything. Even if we unified all four forces, such a theory would rest on assumptions, mathematical structures, symmetries, principles taken as given. We could always ask why that particular theory, why that mathematics, why anything at all. Perhaps the quest for ultimate explanation is inherently endless, each answer raising deeper questions. We don't know what else we don't know. The history of physics is partly a history of discovering that previous theories were incomplete. Newtonian gravity worked beautifully until it didn't. Classical electromagnetism seemed complete until quantum mechanics revealed its limitations. The Standard Model is enormously successful, but clearly incomplete. It doesn't include gravity, or dark matter, or dark energy. What revolutions await? What phenomena haven't we observed yet? What concepts haven't we invented? Future physicists might look back on our current understanding the way we look back on Aristotle's physics. Well-intentioned, sometimes insightful, but fundamentally limited by conceptual frameworks that missed crucial aspects of reality. This isn't a counsel of despair. It's an acknowledgement of the ongoing nature of science. We know vastly more than our ancestors did. Future generations will know vastly more than we do. Knowledge accumulates, each generation building on previous achievements while discovering new mysteries. The forces themselves will continue operating regardless of human understanding. Gravity will keep shaping space-time. Electromagnetism will keep driving chemistry and light. The strong force will keep binding nuclei. The weak force will keep transforming particles. Nature doesn't need us to understand it. But we benefit from understanding, from seeing deeper patterns, from appreciating the elegant structure underlying appearances. Let's pause here and breathe. Mystery isn't failure, it's invitation. Each unknown is an opportunity for wonder, for curiosity, for exploration. The forces we understand are remarkable enough. The mysteries that remain make the universe even more intriguing. As we approach the very end of our journey, let's gather everything together. Let's reflect on what the four forces mean, why they matter, and how this knowledge might enrich your sense of existence as you drift towards sleep or continue pondering in quiet wakefulness. Why does the universe exist? It's the question we began with, whispered softly like a child wondering why there's something rather than nothing. And after wandering through gravity, electromagnetism, the strong force, and the weak force, we find ourselves back at the beginning, still wondering, but perhaps with deeper appreciation. We've learned that the universe exists because four forces work in concert, creating conditions for matter to be stable, stars to shine, chemistry to flourish, life to emerge. Gravity gathers matter into stars and galaxies. Electromagnetism creates light, chemistry, and the visible world. The strong force binds nuclei and powers stellar fusion. The weak force transforms particles and created the matter-antimatter asymmetry that left some matter behind. We've explored how these forces shaped cosmic history, from the Big Bang through the formation of stars and planets to the emergence of life and consciousness. We've seen how they operate at every scale, from the smallest subatomic realms to the largest cosmic structures. We've discovered how they balance precisely, creating a universe fine-tuned for complexity. We've traced the human journey of discovering these forces, from ancient observations to modern experiments. We've pondered philosophical implications, questions of determinism, consciousness, meaning, and existence itself. We've considered how the forces shape your personal experience right now, holding your body together, enabling your thoughts, creating your sensations. We've also acknowledged what remains mysterious: dark matter and dark energy, quantum gravity, the origin of consciousness, the reason for the force's particular strengths, all remain unsolved. The universe hasn't revealed all its secrets. Perhaps it never will. Mystery is part of the package, woven into existence alongside the patterns we've uncovered. Maybe the four forces don't fully explain why the universe exists. Maybe there are deeper questions. Why these forces? Why these laws? Why anything at all? Maybe existence is simply a brute fact, requiring no further explanation. Maybe we lack the concepts needed to even ask the right questions. Or maybe the existence of the universe doesn't need justification. Maybe asking why presupposes purposes or reasons that don't apply to reality as a whole. Maybe the universe just is, and our task is not to explain its existence, but to understand its nature and appreciate its beauty. The four forces enable everything. Stars wouldn't shine without the strong force. Chemistry wouldn't work without electromagnetism. Large-scale structure wouldn't form without gravity. Matter itself wouldn't exist without the weak force preventing complete matter-antimatter annihilation. Each force is necessary. Together, they're sufficient to create the rich, complex, fascinating universe we inhabit. You are a product of these forces, a temporary configuration of matter and energy arranged in patterns that permit consciousness and wonder. The atoms in your body were forged in stars through strong force fusion. The chemistry of your cells depends on electromagnetic interactions. Your weight, your relationship to Earth, your sense of down, gravity, the slow transformations of radioactive elements in your tissues, the weak force. So, with all of this in mind, are you still awake? If you are, I hope it's not because this journey was too interesting. Though if it was, well, at least you've learned a few things about why the universe exists and what keeps it from collapsing into chaos. And if you're already drifting into sleep, may your dreams be populated by gentle gravitational waves, softly glowing electromagnetic fields, and peacefully bound atomic nuclei. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Drop a comment and share. Are you perhaps lying in bed in Mumbai at midnight, or listening from a quiet room in Vancouver in the evening, or maybe somewhere entirely unexpected, under the same physical laws that operate everywhere? If you found this gentle journey into the four fundamental forces relaxing or informative, or both, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture that helps me keep bringing you more calming, curious content from the world of physics, astronomy, cosmology, and beyond. Each video is crafted to balance education with relaxation, knowledge with peacefulness. Thank you for joining me on this journey through the forces that make existence possible. Sleep well, dream deep, and may you feel gravity's gentle embrace, electromagnetism's quiet humming, the strong forces' steadfast binding, and the weak forces' patient transformations. The universe has been unfolding for nearly 14 billion years, according to these 4 principles. Tonight, you can rest knowing you understand them just a little better. You don't need to hold on to any of this. Just let it drift away, like clouds dissipating into a clear sky. Remember, you're part of something vast and ancient and ongoing. The forces that shaped the first stars are shaping you right now. The same laws that govern distant galaxies govern your heartbeat. You're continuous with the cosmos, made of star stuff, held together by fundamental interactions that care nothing for human concerns, yet enable everything human. Close your eyes, if you haven't already. Feel your body relaxing more deeply. Notice your breathing, slow and steady, as automatic as the forces that make breathing possible. You're safe, held by gravity, sustained by chemistry, made possible by nuclear binding, shaped by billions of years of cosmic evolution. The forces will continue their work while you sleep. Gravity will keep Earth in orbit around the sun. Electromagnetism will carry information through your nervous system, maintaining your body even in unconsciousness. The strong force will hold every nucleus together. The weak force will slowly, imperceptibly transform particles deep within you and throughout the cosmos. Nothing requires your attention. Nothing demands your effort. The universe operates whether you're awake or asleep, whether you understand it or not. Tonight, you can simply rest, knowing that reality rests on foundations more solid than stone, more reliable than any human creation, more enduring than all civilizations combined. Good night.